Good afternoon, colleagues. My name is Shishkin. Let me present my report titled Lanthanum cuprate as a promising oxygen carrier for CLOU process. Uh, the modern trend for ecological friendly power generation forces the scientific community to develop various approaches alternative to the state-of-the-art technology, including fuel cells, solar power plants, wind engines, etc., despite the majority of electricity generated at thermal power stations, as you can see at Figure 1. Supreme number of fuel is a raw resource. To avoid greenhouse gas emissions, air-free fuel combustion could be applied as an alternative for thermal power station. Chemical looping combustion concept has been offered in the 1951, but only in the beginning of 21st century the method began to develop rapidly. Chemical loop concept illustrated at Figure 3. Oxygen carrier circulates between fuel reactor and air reactor. In the first, oxygen carrier reduces in contact with fuel. It's for chemical looping combustion, or realize weakly bonded oxygen. It's for chemical looping with oxygen uncoupling. In such a way, air-free combustion occurs. After that, oxygen carrier transfers into air reactor, where it reoxidizes for the following cycle. The first suggested OC material was copper oxide, due to its high efficiency to cost ratio. Despite initially promising results within CLOU process, copper oxide using appeared to be problematic because of easily reducing of copper oxide to fusible metallic copper, this leading to undesirable agglomeration and, as a result, the decrease of combustion efficiency. Since then, the most research was focused around copper oxide as an active material with inert material support. Recently, the special attention has paid for perovskites and complex oxides as promising OCs, which have combination of long-term mechanical stability, good fluidization properties, and appreciable reactivity with gaseous fuels. Considering the aforementioned data, it's interesting to examine whether copper-containing compounds with perovskite structure can be applied as OC material, as the stable copper compound lanthanum cuprate was chosen for the study. High-purity copper and lanthanum oxides were selected as raw materials. Lanthanum cuprate was synthesized by a conventional solid-state route. The phase purity of final oxide powder was confirmed by analysis of X-ray diffraction spectrum collected using Shimadzu XRD 7000 diffractometer. The variations of oxygen content in with temperature were determined by means of thermographic metric method using Cetram TG92. Polythermal dependence were recorded consistently in the air media and atmosphere containing 5% of hydrogen in argon. There are several lanthanum cuprates presented in Figure 6 which exist in air. Experimentally, X-ray spectrum for the synthesized oxide is shown in Figure 5. According to the results of Rietveld analysis, lanthanum cuprate is crystallized in orthorhombic symmetry with CMCE space group. The values of unit cell parameters supplied within Figure 5 are in good agreement with literature data. Thermogravimetric experiments show lanthanum cuprate doesn't possess any significant changes in oxygen content at heating in air or argon as depicted in Figure 7. But in 5% hydrogen in argon, lanthanum cuprate loses up to 3.9 weight% at 950 degrees, which could be considered as a good oxygen capacity for CLOU. Single cycle presented in Figure 8 shows no sufficient degradation with oxygen content deviation between 4.1 and 3.15. As a result of the current study, it could be concluded that the Radelsden-Popper phase lanthanum cuprate has a number of desirable properties as an oxygen carrier in the CLOU process. Thanks you for your attention.